Hello, good morning, good evening. My name is Chad Miller, and today I will be presenting to you kinematics, which is a big fancy physics word for the physics of motion. Motion meaning things that are in motion, things that are moving. You can have no motion, which means something's at rest. And you can have things that are moving in a simple motion, and you can have things that are moving in a complicated motion. A simplest motion would be something sitting there by itself. An example of complicated motion would be something like a spring. Right? Some kind of mass attached to a spring that's going to oscillate back and forth and back and forth.
Quick little overview of kinematics. I'll take you through this one by one. The first thing that we're going to talk about are vectors. These are going to be important when describing motion. We also need to talk a little bit about coordinate system, because we need to know where things are, their position, and which direction they're going. After that, we'll talk a little bit about two-dimensional systems, because we live in a three-dimensional world. We'll just only talk about two of those dimensions for simplicity. Next, we'll actually go over the kinematic concepts. This is going to be what we're going to call displacement, speed, also known as velocity. They're slightly different from one another, but we will talk about that, and acceleration. And then after that, we're going to finish it up with graphing motion. We can actually plot on graphs and that describes how something moves around and see it visually. Okay, here we go. So a lot of physics is kind of learning a language. I think a lot of people, just from being alive, know a lot about motion and how things move. But we're going to assign some words, and I'm going to describe a couple of brief little things that will help us communicate about this. The first on the list, which we talked about, is vectors. Now, if something is moving from here to there, we can describe that motion as an arrow. So a vector basically is an arrow. It is a quantity or value that has magnitude, and that's a fancy word for how much, but it also has direction, which is which way. And that's important. The opposite of a vector, which we won't talk about too much, but just for reference, is what we call a scalar. Now, a scalar is only the magnitude. An example of this would be sum of value. So you have $100. That is a value that has a unit on it. Another example of a scalar would be temperature. We say it is 47 degrees Celsius outside. Here is the unit, and there is a value or magnitude of what we're talking about. It does not matter which direction, or there is no such thing as direction for these things, versus a vector has a scalar value or a magnitude, and it also has a direction. An example of this for a vector would be, you say you went a distance of 100 miles. Right? But if you say you went 100 miles west, that would be a vector quantity, because that is different than going from 100 miles east. Next up, we're going to discuss coordinate systems. A very common coordinate system is what's called a Cartesian system, and that is made up of two axes. This could be the x-axis, and this is commonly termed the y-axis. When you're talking about motion, it is important to define a coordinate system. Now, the coordinate system that you define is up to you. It can be whatever you want, as long as it's defined and is known. On the Cartesian coordinate system, there is a horizontal direction x, there's a vertical direction y, and usually the very center here is what we call the position 0, 0, which is also referred to as the origin. This is a two-dimensional coordinate system, but a coordinate system doesn't have to be two-dimensional. We can simplify it first and call or look at a one-dimensional coordinate system. That would be simply kind of like a number line, where you have that direction. That is the positive direction because that is the direction that numbers or values increase. So if something moves from this position and it moves over to this position, it moved in the positive direction. That is different, right? Let's see, from there to there would be positive movement, but you can also have something move from here over to this position, and that would be defined as negative movement, or moving in the negative direction. It doesn't matter, again, what direction is positive, because there's no reason why we couldn't have said that that way to the left was the positive direction, and then in that case all the signs, or positives and negatives, would flip. The motion is the same, but the coordinate system is important. Now, commonly, because of this system here, if you're looking at something on a piece of paper, up is defined as positive, and to the right is defined as positive too. Now again, it doesn't have to be this way, but these are common things that happen so that everyone doesn't have to think too much. Up next, we're going to discuss 2D or two-dimensional vectors. Oops, sorry about that. Let's use a coordinate system like such, like we had up here before, a two-dimensional coordinate system where this is positive x and this is positive y. And let's say this is the origin. Something can move, it's possible for something to move from this position to this position. So we can draw a vector from that position to this position. That's our start point. This is our end point. Here's the vector defining how it moved. Now, in this particular coordinate system, which is horizontal and vertical, it moved in two different directions. There is a component. So that is the same as going from here to here directly as if I would go only in the horizontal direction. And then another move where I went only in the vertical direction. Those two arrows add up to give you the same overall displacement or movement. So this could be a vector in the x direction. This is the x component. And this would be the motion in the y direction, which would be the y component of the overall motion. And these can be split up. Those two add together to give you the motion d. I'm using d for distance in this case. So these two vectors, x and y, because they're vectors because they have a length and a direction associated with them. Those two add up to give us the vector d. And so d, we can say, is equal to x plus y. Now this is different than normal adding or algebra, because x is in a different direction than y. And so what we will usually do symbolically at times, and I want to introduce you to that, is when something is a vector and not just a scalar, we'll put these little arrows on top. And that's just notation to show us that these things actually are not scalars. They are vectors. Next, I want to introduce you to some of the basic kinematic concepts. Now again, kinematic is just a big fancy word for motion concepts. The first is what we're going to call distance, and I think a lot of people are familiar with this, versus what we're going to call displacement. They are different things. Now, a lot of times they can be equal, but they are not, by definition, the same thing. Distance, we can think of as how far you've traveled. Displacement is a change in position. So let me give you some examples here. Here's a map of California. My awesome drawing abilities. And you're going to take a trip. You're going to go from Sacramento, up here, down to Los Angeles. Now, as you drive in a round trip, you're going to start off in Sacramento, you're going to drive down the Highway 5, down to LA, you're going to go to Disneyland or Universal Studios, wherever you're going to go, and then you're going to drive back, all the way back. So you have a round trip that goes. The distance that you traveled is going to be equal to what it says on the odometer of your car. This is how many miles you've traveled total. So on the way down, you traveled 386 miles. This is Sacramento to LA. On the way back, same distance, 386 miles from LA back up to Sac. And so the total distance that you've traveled is 772 miles. That's your distance traveled. In this same situation, though, your displacement is different because you return back to the same place that you started with. So your overall change in position is 0. So let's talk about that for a second. So position is just where you are relative to the origin. And that's the origin of your coordinate system. Okay? So we're going to call the position x. And then some symbology here. This triangle and the x, this symbol right here, always in physics and mathematics, means the change in position. So this means the change in position. And the change in anything is the final position minus the initial position. Okay? This can be abbreviated as XF for final and XI for initial. So your displacement is always the difference between your starting and ending position. So in the case of driving down south and then driving back up, your displacement, or change in position, is 0 miles. You didn't go anywhere in terms of this definition of displacement. Okay, let's do a couple of examples. I'm just going to do a one-dimensional example. So we have some origin right here. That's our 0. This can come out to 1, 3, 4, and 5 meters. So this is in units of meters right here. And if we have an initial position here, which is at a position of 1 meter away from the origin, put an I there for initial, and we travel to a position of 4 meters, that's our final position, then the displacement that we've traveled, change in x, is equal to the final position minus the initial position, which equals the final position. This is where we ended up. We were at 4 meters. And then we're going to subtract off the initial position, which we were at 1 meter. And so our displacement, or change in position, is 3 meters. Now this is also our distance. The distance is the same in this particular case, because we've gone 1, 2, 3 meters for our distance. But distance is not a vector. Displacement is. So let's do a similar example where we have the same number line, x in meters. But now, our initial position is going to be over here at 4. This is where we're going to start. And we're going to travel over time to a position of 1 meter away from the origin. And that will be our final position. So in this case, our displacement, which is the change in position, which is also the final position minus the initial position, is equal to 1 meter, because that's where we started, or sorry, our final position, which is at 1 meter, and we're going to subtract our initial position, which was at 4 meters. Now this is different. This is going to be 1 minus 4, which is negative 3 meters. That is our displacement. Okay? So the displacement is negative 3 meters. The distance that we moved in this situation is just 3 meters, because we went 1, 2, 3 meters. The displacement is the vector quantity, which has the negative, which tells us the direction that we went to the left. The distance does not contain that information.